Hi children, welcome to today's physics class. Today we will do few more problems from the chapter Laws of Motion. Let's move on to the first question. A monkey of mass of 40 kg climbs on a rope which can stand a maximum tension of 600 Newton. In which of the following cases will the rope break? The monkey climbs up with an acceleration of 6 meter per second square, climbs down with an acceleration of 4 meter per second square, climbs up with a uniform speed of 5 meter per second, falls down the rope nearly freely under gravity, ignore the mass of the rope. So in the particular question, you can see from the picture a monkey is climbing on a rope, and this rope can withstand or can afford a maximum tension of 600 Newton. We have to check by considering the following situations. What is the tension offered by the string in each of these cases? And by finding the value of tension in each of these cases, we have to compare that tension with the maximum value of tension, and we have to check in which case the rope will break. Right. So the problem is very simple. By drawing the free body diagram, we can easily find out the value of tension offered by the string in each case. So let's write down the given parameters. The first thing, the mass of the monkey is given, that is 40 kg, and the maximum value of tension that the string can afford is also given, that is 600 Newton. So we have to check the value of tension in each of the cases. First I am taking the case 1. So in case 1, the monkey is climbing up with an acceleration of 6 meter per second square. The acceleration is given 6 meter per second square. So let's draw the free body diagram. Before drawing the free body diagram, roughly I am drawing the given situation. Assume that this is monkey. Okay. And how many forces are acting on monkey? The two forces. One is the weight of the monkey, which is acting along the downward direction, and the next force is the tension in the string, which is acting along the upward direction. So only two forces are acting on monkey, that is mg downward direction and the tension T. Now we have to apply Newton's second law in this equation, that is the net force experienced is equal to the mass into acceleration. And since the monkey is climbing up, while writing the net force I have to write the tension first. So T minus mg is equal to m into A, or T is equal to m into g plus A. Okay, I am taking this negative mg to the right hand side. Since m is common, that I took outside. Now substitute the values. Mass is 40, g now we can take 10, and acceleration is given 6. So the value of tension T will be equal to 40 into 16, which is equal to 640 Newton. Right. So when the monkey is climbing with this much acceleration in the upward direction, the tension in the string is 640 Newton. So now let's compare this tension with the maximum value of tension. The maximum value of tension is 600, but now the tension offered in the string is 640. That means the tension in the string exceeds the maximum affordable tension in the string. So in this case the rope will break. When the monkey is climbing with this much acceleration, the rope will break because the tension in this case is greater than the maximum tension of the rope. Okay. Now let's move on to the second part, B part of the question. The monkey climbs down with an acceleration of 4 meter per second square. So again, drawing the free body diagram, the weight of the object is acting along the downward direction. The tension is acting along the upward direction. And here the acceleration is given as 4 meter per second square. Again we have to apply Newton's second law here. Now in this situation the monkey is climbing down. So I am writing the mg first mg minus t is equal to mass into acceleration, and I need to find out what is the tension T. So T is equal to m into g minus a. Right. I took this T to the right hand side and I took ma to the left hand side, and I took this mass common, and mass is given 40 and g is 10 and a given 4. So tension offered by the string is 40 into 6, which is equal to 240 Newton. Now in this case the tension is less than the maximum value of a tension that the rope can afford. So definitely the rope will not break in this particular situation. Yeah, maximum value is 600, but in this situation it is 240 only. Now the third situation, the monkey climbed up with a uniform speed of 5 meters per second. That is, here acceleration is equal to 0. It is moving with a uniform speed. Again, we have to draw the free body diagram. The mg acting along the downward direction and the tension is acting along the upward direction. Here it is climbing up. So I am drawing the tension first. I am writing the tension first, and mg equal to no acceleration. So this is equal to 0, and tension T is equal to m into g. Right. And T is equal to mass is 40 and g is 10. So here in this case we are getting the tension as 400 Newton. So in this situation also the tension is less than the maximum value of a tension, so the rope will not break. Now the fourth situation. In the fourth situation, the monkey falls down the rope nearly freely under gravity. Okay, if an object is falling down freely under the gravity, the acceleration of the object will be acceleration due to gravity. A will be equal to g in this particular situation. So here also if we are drawing the free body diagram, the mg will be acting along the downward direction and the tension will be acting along the upward direction. Right. If an object is falling freely under gravity, the acceleration will be equal to acceleration due to gravity. So it is falling down. So this mg minus t is equal to m into a. From this t is equal to m into g minus a. Okay, and m is 40 and g is 10 and acceleration is 10. Here the tension will be equal to 0. So the monkey in this situation also the rope will not break. Here the tension is 0 because it is just like falling under gravity, that situation. Okay, so given among the given 4 situations, only in the first situation the rope will break because when the monkey is climbing up with an acceleration of 6 meters per second square, the tension offered is greater than the maximum value of tension that the string can afford. Okay. Now let's move on to the next question, and this question is almost similar to the previous problem of that monkey and rope problem. A man of mass 70 kg stands on a weighing scale in a lift which is moving upwards with a uniform speed of 10 meters per second, downwards with a uniform acceleration of 5 meters per second square, upwards with a uniform acceleration of 5 meters per second square. What would be the readings on the scale in each case? What would be the reading if the lift mechanism failed and it hurtled down freely under gravity? Right, so this problem is almost similar to the before problem. In this question, the given a man is standing in a lift with a weighing machine. So when the lift is moving with a different acceleration and a different speed, the measurement of the weight shown by the weighing scale is different. So we will call that weight as the apparent weight. So here we have to find out what is the apparent weight shown by the weighing scale when the lift is moving with a uniform speed with acceleration 5 meter per second square, and when it is moving downward with an acceleration of 5 meter per second square. So how to measure the apparent weight? This apparent weight measured by the weighing scale will be equal to the normal reaction provided by the floor of the lift. So in this situation we have to find out what is the normal reaction. By drawing the free body diagram we have to find out what is the normal reaction. Okay. So the given parameter is the mass of the man. The actual mass of the man is given 70 kilogram. We have to find out what is the apparent weight of the person. Right. So we have to consider the free body diagram. Take the first situation. I will write here. Okay. The first case. In the first case, the lift is moving upward with a uniform speed of 10 meter per second. That is, in the first case, the acceleration is equal to 0. Now we have to draw the free body diagram. First I will draw a rough diagram. Assume that this is the lift cabin and the person is standing here, and the weight of the person is acting, the forces acting are the weight of the person acting along the downward direction. Okay. And the next force is the normal reaction acting. This is the normal reaction. So these are the two forces experienced by the person when the person is standing inside a lift. Next thing is we have to apply Newton's second law in the given situation. So F net is equal to mass into acceleration. Right. Since in the given situation the lift is moving upward, I will write the normal reaction first. So N minus mg is equal to ma, and here acceleration is equal to 0. So N is equal to mg. The normal reaction will give you the apparent weight measured by the weighing balance or weighing machine. So from this normal reaction is equal to mass is 70 kilogram, and if we are taking G as 10, we will get 700 Newton. 700 Newton is the normal reaction, and we have to convert this into apparent weight. That is, the apparent weight will be equal to, apparent weight is equal to 700 divided by G, that is 10, which is equal to 70 kilogram weight. Okay, 70 kilogram weight. This is the force. From this we have to calculate what is the apparent weight. For that 700 divided by G, acceleration due to gravity, we will get the answer 70 kilogram weight. Now the next situation is the B part of the question. The lift is moving downward, downward with a uniform acceleration of 5 meter per second square. So now here the lift is having an acceleration which is equal to 5 meter per second square. Again we have to draw the free body diagram. Again the two forces are acting, mg along the downward direction and the normal reaction along the upward direction. Since it is moving downwards, the equation will be mg minus normal reaction is equal to m into a, and we have to find out what is the normal reaction. Normal reaction is equal to m into g minus a, and which is equal to mass is 70 kilogram into g is 10 minus acceleration is 5. So we will get a normal reaction as 70 into 5, which is equal to 350 Newton. From this the apparent weight is equal to 350 divided by acceleration due to gravity, which is equal to 35 kilogram weight. Right. Now moving on to the third situation. The third situation, the lift is moving upward with a uniform acceleration of 5 meters per second square. So here the lift is having an acceleration, and again this is the free body diagram. mg acting downward, the normal reaction upward. Here the lift is moving upward, so I am writing I have to write the normal reaction first. So the normal reaction minus mg is equal to m into a. From this normal reaction, n is equal to m into g plus a, or n is equal to 70 into 10 plus 5. That is, n is equal to 70 into 15. From this, I will get n is equal to 105 Newton, or apparent weight is equal to 105 divided by 10, which is equal to 10.5 kilogram weight. Sorry, not a 10, not 5, it is 1050. Okay, I forgot to put the 0. So here the answer is 105. Here 105 kilogram weight. Okay, now we are moving on to the fourth situation. In the fourth situation, what would be the reading if the lift mechanism failed and it hurtled down freely under gravity? So this is similar to the situation that we did in the case of a monkey problem. In the third situation, when the lift mechanism failed, it will move under gravity. So there the acceleration will be equal to the acceleration due to gravity. So when I am applying the Newton's second law in that situation, mg minus n equal to ma, and from that n is equal to m into g minus a, or n is equal to m into 10 minus 10, which is equal to 0. That is, if the lift mechanism failed and if the lift is falling down, the object will experience a freely falling feeling, that is weightlessness. Okay. So when the lift is moving upward with a uniform speed, the apparent weight was 70 Newton. When it is having acceleration, when it is moving down, it is having an apparent weight of 35. And when it is moving, what was the B part? When it is moving downward with an acceleration, it is having an apparent weight of 35. When it is moving upward, it is having an apparent weight of 105. So if we are moving in a machine in the downward direction with a uniform acceleration, the apparent weight will decrease, and in the case when we are moving upward with a uniform acceleration, our apparent weight will increase. Right. This is the equations. N is equal to m into g minus a. N is equal to m into g plus a. If we are moving up, this one. If we are moving down, this one. Okay. Now let's move on to another type of a question. The problem is two bodies of masses 10 kg and 20 kg respectively kept on a smooth horizontal surface which are tied to the ends of a light string. A horizontal force F is equal to 600 Newton is applied to object A first, then object B along the direction of the string. What is the tension in the string in each case? So the figure is not given, we have to draw the figure. So we have two blocks with masses 10 kg and 20 kg. We can take the block with mass 10 kg as object A. Right. So let MA as the let MA is the mass of the object with a 10 kg and MB is the mass of the object with 20 kg. Okay. Now these two objects are resting on a smooth horizontal surface. That means there is no friction between the blocks and the floor. Yeah, we'll draw the situation. These two are resting on a smooth horizontal surface. And these two are tied to the ends of a light string. By light string we are meaning that it is a massless string. It is inextensible. Okay. So this is block A and this is block B. A horizontal force is applied first to object A and then to object B. We have to find out what is the tension in each situation. Right. So first we will discuss the first case. In the first case we are applying force on object A along this direction. We have to calculate what is the tension in the string in this case. Okay. So we have to draw the free body diagram, draw all the forces experienced on the object. So the forces acting along this direction and the tension from this point will be acting along this direction. From this point it is acting along this direction. And we will have the normal reaction and weight of the object along the vertical direction. Okay. Now we have to apply Newton's law here. So the forces acting on object A are the mg which is acting along the vertical direction and normal reaction, and one force applied force F is acting along this direction. The tension is acting along this direction, and there is no acceleration along the vertical direction. And when we are taking the block B, the mg is acting along the downward direction, the normal reaction which is acting along the upward direction, and the tension is acting along this direction. These are the forces. Okay. Now let's apply Newton's second law for block A and for block B. We have to calculate what is the tension. So when we are applying Newton's second law along the horizontal direction, we can write the net force is F minus T, which is equal to M into A. So here this F is not the net external force. This is the external force applied on the block A. That is given as 600 Newton in the question, and let this be equation number 1. We have to calculate what is the tension, but look at the equation. The acceleration of the system is also unknown. So we have to find out acceleration first to calculate the value for tension. So for that we have to apply Newton's second law on the block B. When we are applying Newton's second law on block B, we can write the expression, the net force, only one force is acting along the horizontal direction. So T is equal to M into A. Let this be equation number 2 for block B. We applied Newton's second law on block B. We are taking only the horizontal direction. The vertical direction we are not applying. N is equal to mg. Along the vertical direction, N equal to mg. No acceleration along the vertical direction. Okay. Now add equation number 1 and 2. When I am adding equation number 1 and 2, this is This is MA and this is MB. Right, this is MB, this is MA. This is equation number 2. And when I am adding these two equations, this T will get cancelled and I will get the F external is equal to MA plus MB into A. So from this, acceleration A is equal to the external force applied on block A divided by MA plus MB. Right, which is equal to external force they given as a 600 Newton in the question divided by mass of block A is 10, mass of block B is 20. So acceleration A is equal to 600 divided by 30, which is equal to 20 meter per second square. So this is the acceleration for the system when we are applying a force F equal to 600 Newton to block A. Okay, now we got the value of acceleration. Next we have to calculate what is the tension in the string. To calculate the tension, either we can put the value of acceleration in equation number 1 or in equation number 2, because in both the case the tension is the same. So I am applying the acceleration in equation number 2. Easily I can calculate what is the tension. Tension T is equal to MB into A, which is 20 into 20. That is, tension in the case is 400 Newton. Okay. Now this is the first situation. Now we are moving on to the second situation. In the second situation, what we are going to do is we are applying, I will draw the direction in the same figure. In the first situation, instead of applying force on A, we are applying force on B along this direction. Okay, we are applying force along this direction. And all the other force will be same here. This force will not be there. Now we are applying the external force on block B. Okay. So I will draw the free body diagram for block A and B. For block A, now the forces acting are the mg and the normal reaction and tension which is acting along this direction. And when we are taking block B, the forces acting are the mg along this direction, the normal reaction along this direction, the applied external force along this direction, external force, and the tension in the string acting along this direction. Okay. So we have to again apply Newton's second law here. The net force experienced is equal to F net is equal to M into A. Along the horizontal direction I am applying. For object A, only one force is acting along the horizontal direction. So T is equal to MA into A. And this will be equation number 3. And when I am applying Newton's second law along the horizontal direction for block B, I have two forces here. So F external minus T is equal to MB into A. Let this be equation number 4. And from this expression, to calculate the tension, I need to find out the acceleration, and the acceleration will be same in both the cases. Whether we are applying the force on block A or on block B, the acceleration of the system will be same. And if you have any doubt, you can check it from equation number 3 and 4. The T will get cancelled out and the F external will be is equal to MA plus MB into A. We are getting the same expression for calculating the acceleration. A is equal to F external divided by MA plus MB. Right. You can see the same equation. Whether we are applying force on block A and on block B, the acceleration of the system will be same. But there will be a change in the value of tension. Now look at the equation of tension. To get the value of tension, I have to apply the value of acceleration in any of these cases, in any of this equation. So I will get the tension T equal to, when I am putting the value of acceleration in this equation, T will be equal to MA is 10 and acceleration is 20. So in this case the tension is 200 Newton. So what we can conclude from this? The tension depends upon which mass enters, on which mass end the force we are applying. Depending upon that, the tension developed in the string will change. In the first case, we applied force on block A, and in that situation we have the tension as a 400 Newton. But when we applied the force, external force on block B, the tension become 200 Newton. So depending upon in which direction or on which block we are applying the external force, the tension developed in the string will change, but the acceleration of the system will remain the same in both the situations. Okay.